everyone else can hear me. Uh, oh, there we go. Some people coming still, but I guess I'll just get started. Yeah, so hi everyone. My name is Darwin. I am a PhD candidate at Adelaide Uni, funded by the MINEX CRC and the ARC Linkage Partnership. I work closely with Alan Collins, URI Forecash, Morgan Blades, as well as Amber Jarrett from Geoscience Australia. And like Alan mentioned, today I'll be doing my PhD major review, sort of giving everyone an update as to what I've been doing for the first 10, 11 months of my PhD, and letting everyone know what my plans will be for the rest of my candidature as well. And to start off with, I just want to thank the industry, government, and academic partners who are collaborating and supporting me on this project. And I want to start off with taking a step back and talking about why sedimentary rocks are important to us. So sedimentary rocks only make up a small percentage of the Earth's crust, but is a key archive for understanding how the Earth's atmosphere, biosphere, and hydrosphere evolved through time. And I always like going back to this figure from Leon et al. 2014, in which they nicely summarize how we think oxygen in the Earth system has developed. So we just have time on the horizontal axes and oxygen levels in the atmosphere in the vertical axes. And the faded red curve here showing the historic classic two-step view of how we used to think oxygen in the atmosphere evolved. In the blue curve, we have the, I guess, more recent emerging model, sort of showing how we think atmospheric oxygen evolved now. And evidence for all of these interpretations are all anchored in the geochemistry of sedimentary rocks. In the Archean, we had evidence for whiffs of oxygen through organic rich shales and banded iron formations. So organic matter will have undergone photosynthesis and produced oxygen in the water column. And most of that oxygen was probably being taken up by sinks in the water column, like reducing iron compounds, which would precipitate hematite and form banded iron formations. Over time, at around 2.5 to 0.4 GA, the source sink balance of oxygen tipped in the favor of oxygen accumulation. And again, we have evidence for this in our sedimentary rocks with the disappearance of redox-sensitive detrital minerals like uraninite and apatite, as well as this big smoking gun, which is sort of the absence of mass-independent fractionation of sulfur isotopes. I don't want to get too much into it, but we need a certain level of oxygen in the atmosphere for these things to occur, essentially. And in the Phanerozoic, we had the secondary oxygenation event and the Cambrian explosion as well, where we have the diversification of biological life. Essentially, things got bigger, more diverse, more unique. And we also have changes in redox-sensitive isotopes and elemental tracers in our sediments. And all of that evidence point to another jump into sort of present-day atmospheric oxygen levels, really. And the biological diversity in the Cambrian is also key to anchoring the chronostratigraphy and isotopic framework in this time interval. But what I want to focus on is a big chunk of the Proterozoic, especially the Mesoproterozoic, which has been commonly associated with a period of general stability within the Earth system. The era has largely been defined by relatively unfluctuating atmospheric oxygen levels, shown here by the red line, and previous investigators have coined it the boring billion, really. However, as we see, recent emerging models suggest that things may not be as simple as they seem. We have the big blue bar in the figure showing how poorly understood this time interval is, and implies oxygen could vary anywhere between these levels. So have massive implications for how early biological life will evolve through this time interval. And these are just some geochemical proxies from shales and carbonates that have been used to understand and model how we think the Earth redox system evolved through time. And the reason why the Mesoproterozoic is so poorly understood is that we just have massive gaps in the data set compared to other intervals in Earth's history. Which leads me to my project, really, which is the sedimentary geochemistry and geochronology of the Greater MacArthur Basin. Now, the Greater MacArthur Basin is a super basin system deposited across large parts of northern Australia. And the basin records 1 billion years worth of Earth's history from about 1800 MA to the Devonian. as such as an integral geological archive for the Mesoproterozoic era. The sediments are exceptionally thick and relatively low grade, which is important in preserving primary signals from seawater, and overlies the North Australian craton, with surrounded by exposed basement and origins west, south, and east of the basin system. The northern basin boundary is actually relatively unknown, and it's been thought that the Yanshan Basin in the North China Craton may have well been contiguous with the region at the time of deposition. And the basin system consists of sediments from smaller subbasins, such as the Birndudu Basin, bits of the Tonkinson Province, the South Nicholson Basin, as well as the proper MacArthur. But for this talk, I just want to focus on samples from the Birndudu Basin and the MacArthur Basin. Now, the super basin system is categorized into different packages, which are just basin scale rocks that look similar, have similar ages, and similar stratigraphic positions. And as such, similar sediments at different locations are called different things. So essentially, we need a better chronological framework to anchor any geochemical interpretations we make. And hopefully from that, we can systematically analyze each temporal package for its shale and carbonate geochemistry, and therefore help us reconstruct past paleoenvironments and illuminate how the Earth system evolved through the time. Which brings me to the main themes I'll be exploring in my talk today. And the first theme I'll be looking at is to try to improve the chronological framework of the basin system. And I'll be doing that by trying to develop a new application of in situ rubidium strontium dating for shales. The second theme I'll be exploring is the investigation of paleoenvironment conditions and establishing inter-basin correlations with the use of regional scale strontium and carbon isotope chemostratigraphy. And my third theme is trying to constrain redox conditions in the water column of the basin system using a multi-proxy approach of different redox sensitive trace elements. And just before I continue on, all of these are very much integral to one another, really. We need a solid time framework to make any reasonable interpretations. A chemostrat can be a super powerful tool as a pseudo-dating method without the use of a biostrat. And obviously changes in paleoenvironment have massive controls and how the redox conditions change as well in the water column. And for this talk, I'll be focusing on these 6 different drill holes, where the symbols for these drill holes just match up the main themes I'll be investigating today. So for my first theme, I'm trying to improve a chronological framework for the basin system. As such, knowing the timing of when these sediments form is really important for any further interpretations. And for this next set of results, I'm trying to focus on the Roper group, and particularly samples from UofA 5 and UofA 6 drill holes. And the Roper group is just part of the Wilton package, which is the youngest of the coherent basin phases. And it's mostly made up of marine siliciclastic sediments, with the younger Miawok subgroup more abundant in organic rich shales. And the older Kolara subgroup made up of things like mud rocks, carbonaceous shales, and likely deposited to be in a shallow marine shelf environment. And on the left-hand side here, we just have a simplified strat log of the Roper group, along with some of its age constraints. And we have the Derm event shown here in this brown sill thing, which is a dolerite intrusion cutting through most of the units in the Roper group. And then it's been dated around to be around 1313 MA. Like most, if not all, Precambrian sediments, a lack of unique fossil records and a robust chemostratigraphy means that these rocks are poorly chronologically constrained when comparison to the Phanerozoic sediments. Age constraints are mostly limited to things like the trilozircons, shown here in red, which is important for understanding what's being deposited into the basin, but only provides us maximum depositional ages. We also have things like cross-cutting relationships and dating interbed volcanics, which is probably the most precise way of dating these sediments. But obviously, these certain geological criteria have to be met for these methods to be viable. And sometimes they are just far and few and far in between, really. And I guess the most popular dating method for Precambrian sediments is probably rhenium-osmium dating of organic rich rocks. Although this method also have problems in of itself. It's pretty expensive and time consuming, and sometimes it just doesn't work because we have very limited amounts of rhenium in the natural environment. Therefore, I'm trying to develop a new method of dating sediments to help improve this time framework, and that's this in situ rubidium-strontium dating of shales. So rubidium commonly substitutes for potassium, sodium, and calcium. But the historic problem with beta decay dating system like rubidium-strontium is that the mass of the daughter and parent isotopes were the same. This meant that we had to undergo procedures like whole rock digestion and column chemistry to separate the two isotopes, which was an expensive procedure, time consuming. You needed a lot of sample, and doesn't allow us to identify where our rubidium and strontium came from. So we would be subject to secondary input of rubidium and strontium from things like detritus or diagenesis. However, recent developments in technology has allowed the installation of a reaction cell between two quadrupoles and a mass spectrometer to resolve this mass balance issue. A reaction gas can be introduced, which reacts with one isotope and not the other, so that we can distinguish the mass interference between the parent and daughter isotopes. In situ analyses can also provide textural context, so we can avoid things like big detrital grains, but also concurrently collected data along with rubidium strontium analyses can help categorize the geochemistry of each sample. So the first drill hole I'll be discussing in this case study is UofA 6. Its mineralogy shown in the high logger mostly consists of things like quartz and aluminosilicates, pretty common for siliciclastic sediments. And I've sampled here the UR6269, which is a shale chip from the Gibb member of the Minor Formation. The second drill hole I'll be talking about is UofA 5, and the biggest difference from UofA 6 is that the sediments in UofA 5 has been intersected by the Darwin dolerite. And another massive difference is the mineralogy, highlighted by the high logger again. And in this drill core, we have an abundance of high temperature minerals, such as chlorite, shown in green. I've taken 3 samples from this drill hole, UR5139 from a shale from the Jalboy Formation, UR5229, chip from the Darwin dolerite, and UR5329, another shale from the Crawford Formation. We've also analyzed these samples using bulk XRD, and gives us similar results really, with the UofA 5 shales, giving us an abundance in high temperature minerals like chlorite, in particular pictat, chamosite, and clinochlor. On the other hand, the UofA 6 shales are absent of these high temperature minerals. So already we have substantial evidence for the UofA 5 rocks to have experienced higher temperatures compared to UofA 6. And as such, I guess we already have our hypotheses being that perhaps the UofA 5 samples have rubidium strontium system. They may be reset by the secondary thermal event, probably caused by the Darwin intrusion. On the other hand, the UofA 6 drill core, which is not intersected by the Darwin, may still preserve primary rubidium strontium systems during the deposition of these shales. So the first result I want to discuss is the UofA 6 Minor Formation shale. The age of the sample is 1576, pretty bang on to what we expect for deposition age, around 1.5 GA. And what's also very interesting is that the initial calculated ratio of A7A6 strontium from the isochron is also very accurate to what we expect for strontium isotopes in seawater at the time. Next, we have the UofA 5 results. So the samples from both of the shales are around 1300 MA, which overlaps with the age of the Darwin sample. And again, what's also interesting is that unlike the UofA 6 shale, the initial ratio calculated by the isochron is a lot more elevated when compared to seawater. And instead, these shales have initial ratios reflective of the Darwin dolomite. The post-Archean Australian shale normalized values of the UofA 6 minor formation is shown here in blue and is relatively flat, which is consistent with what we expect for a primary whole rock rare earth analysis of ancient shales. As such, with the pristine mineralogy from the XRD and the high logger, as well as a pretty accurate age and initial ratios from our isochrons, as well as this pristine rare earth signal, we're pretty confident that the UofA 6 shale sample are recording primary orthogenic signals, perhaps from minerals precipitating in equilibrium with the seawater at the time. On the other hand, the UofA 5 shales have rare earths, light rare earth depletion, more akin to its nearby dolomite counterpart. And again, furthermore, with the ages and the initial ratios overlapping very much so with the Darwin dolomite, as well as the presence of high temperature minerals picked up in the high logger and bulk XRD data, we're pretty confident that these shales are instead recording a secondary thermal event, most likely caused by the intrusion. And this is a pretty powerful tool, and it has, I guess, a lot of implications, because not only can we get age data of this method, we can also get elemental data that can help us fingerprint the geochemistry of these samples. And that's very useful because we can quickly use this as a screening tool for things like alteration and diagenesis. And for example, this paper here by Shin et al., 2003, have used the UofA 5 drill hole for primary redox analyses. And like we previously discussed, it seems that the rubidium strontium analyses done on these shales from this sample, from this drill hole, has shown that the sediments in this drill hole has undergone a secondary thermal event. Therefore, what's most likely to happen is that this study is instead recording diagenetic signals as opposed to primary seawater values. And again, this has massive consequences because this paper is one of the most cited and, I guess, foundation on which there's people quoted to have seen evidence for oxygenation during the Mesoproterozoic. And just to quickly summarize, it's possible to determine chronological constraints as well as geochemically fingerprint samples using the in situ rubidium strontium dating method. And hopefully in the near future, we can improve some of the errors in our results by perhaps developing improved standards or using a more sensitive equipment like a multi-collector mass spectrometry. And moving on to my second theme, I'll be trying to investigate Palaeoenvironment and establish inter-basin correlations in the McArthur Basin. And to do that, I'll be using two main isotopic systems. The first one being strontium isotopes and carbonates. And strontium isotopes and carbonates track the strontium ratios of seawater, which is mainly controlled by by input from continental weathering, which will give us more radiogenic strontium values, so higher ratios, and hydrothermal fluxes, which will give us juvenile or lower ratios, essentially. And by comparing our samples with the global strontium isotopic curve at a certain time interval, we can use this as a pseudo dating method and also infer relative connectivity and restriction of the basin system from the open ocean. The second isotopic system I'll be using are carbon isotopes, and carbon isotopes and carbon rocks record the dissolved inorganic carbon pool in seawater. And this carbon pool in seawater is fractionated through biological processes, in which biological processes prefer to take lighter carbon isotopes. As such, we can infer things like biological productivity and organic burial rates through the secular changes in our carbon isotopic system. And again, both of these trends can be used to constrain paleoenvironment and productivity in the basin systems. And in addition, systematic trends in isotopic signals can also be used to correlate geographically distant sedimentary sequences without the use of biostratigraphy. And therefore, hopefully we can try and determine changes in isotopic signatures and see whether those changes are caused by regional scale, basin scale variations in paleoenvironment, or perhaps more localized events. And for the second theme, I'll be focusing on results from the Limbunya group, sampled in the drill core LV09001, and this glide package equivalent MacArthur group in the Manbulu S1 drill core. Both groups consist of similar sequences of stromatolites, carbonate platforms, and siliciclastic sequences interbred with organic rich mudstones. So I'll be starting off with the Limbunya group in LV09, and I'll be using changes in paleoenvironment inferred through sedimentology from Schmidt 2015, which is very well reflected in the isotopic record. And the color of the box of the images just correlate to the color of the formation here. And at the bottom, we have the Amaruga Dalstone, consisting of basal dolomites with things like matrix-supported breccias we see in the picture. And the deposition environment interpreted by Schmidt 2015 is supposed to be an open, shallow marine environment. And consequently, we have strontium and carbon isotopes pretty reflective of seawater marine at the time. Moving up through the drill core, we have lower bits of the Barney Creek Formation, where paleoenvironment has been interpreted to have undergone sea level fall with a restriction of water exchange and essentially water stratification, leading to the deposition of these black and organic rich mudstones. And consequently, we see more radiogenic strontium isotope values. And at the top of the Barney Creek Formation, paleoenvironment was interpreted to have undergone sea level change again, which allowed for flooding of a previously restricted environment, which is seen by deposition of more carbonates and dalstones. And as such, we see a secular change of strontium isotopes becoming less radiogenic and more akin to seawater. And right at the top of the drill core, we have the Hot Springs member and the Donegan member, consisting of mainly dolitites, stromatolites, chert nodules, and things like gypsum nails here, which suggested evaporation in a restricted environment, perhaps even coastal lagoon. And again, we see secular change in strontium isotopes becoming a lot more radiogenic, and see similar excursions in carbon isotopes like we see in the lower bits of the Barney Creek. And we can use these isotopic excursions to establish correlations with similar sediments that are far away from each other. So the Manbulu S1 drill core is around 500 kilometers away from the LV09, but we still see similar patterns in isotopic excursions. So we can start to infer whether the changes in paleoenvironment are perhaps more regional and basin scale changes. And these are just purely geochemical correlations. And I think it'll be very helpful in the near future if we start to fill in the gaps in this data set. And I guess to even better constrain these correlations, use sedimentological observations in the Manbulu S1 drill core, as well as perhaps actual geochron data. And I guess to quickly summarize again, it's possible to determine correlations and variations with the two isotopic systems. And from that, we can hopefully try to infer localized and regional scale changes. And I think in the future, hopefully improve those correlations with a bigger data set. I guess for my last theme, I'll be trying to constrain the redox conditions in the water column during the deposition of the Redbank package. And for this bit of my talk, I'll be focusing on the results from the Tawala group of the Redbank package, which is the oldest stratigraphic subdivision of the southern Makata Basin. It's extremely exposed in the Baton Fault zone and overlies basement units from the Murphy province. And I'll be focusing on samples from these two particular drill cores, MCDD 0003 and 0005. I'll be mainly focusing on these three units. So the Whirly Wincha member of the Wunan Manchala sandstone, which underlies the Wollograng Formation and consists of fine-grained sandstones and mudstones. The Wollograng Formation, which is deposited around 1700 MA, consisting of interbed calcareous siltstone and sandstone and organic rich mudstone, and the Malapunya Formation from the lower bits of the McArthur group, which is again consisting of dolomites, stromatolites, and interbedded sandstones too. I'll be constraining the redox conditions of these sediments using two different redox sensitive models. Sorry. The first one being the covariation and trace element enrichment, along with total organic carbon, as well as vanadium and molybdenum ratios. And a multi-proxy approach is important because not only can we develop more robust and confident interpretations, but we can also try and tease out these complicated redox histories in the water column. All right, so in the first model, I'll be using uranium as an example for a redox sensitive trace element. And in this oxidized state, uranium is readily soluble in seawater. However, under anoxic conditions, uranium is enriched in sediments through the formation of organometallic complexes, which is why in anoxic water columns, you have a strong correlation between, say, uranium enrichment and total organic carbon increase. In eusinic conditions, uranium is enriched again, but the covariation with TOC breaks down because free hydrogen sulfides in the water column can also become sinks for uranium. And here it seems like the Malapunya Formation, shown in bronze, and the Whirly Wincha member, shown in gray, seems to show consistently homogeneous, almost dysoxic water redox conditions. On the other hand, Wollograng Formation from both samples show a much more heterogeneous redox history, ranging from dysoxic to eusinic. And that's very interesting because now we can start to infer whether those changes are perhaps temporal as opposed to spatial, because we see these similar trends in the two different drill cores. So in the second bit, I'll be using a different redox proxy, vanadium and molybdenum ratios. So vanadium is essentially enriched in sediments in anoxic water columns, whereas molybdenum is more enriched in eusinic water columns. And here, again, different redox proxy, but telling us a similar story, right? So we've got the Malapunya Formation and the Whirly Wincha member, essentially limited to dysoxic and anoxic conditions, whereas the Wollograng seems to have a more heterogeneous water column redox history. And could these relatively more free sulfide poor and oxygen rich pockets be vital for evolution in early biological life? And I guess this raises the question, what controls these secular changes in redox stratification? And again, are these changes temporal or spatial? And what's also interesting is that we see a base metal enrichment coinciding with the increase in abundance of redox-sensitive trace elements. Now, a lot of these base metals are also redox sensitive, and I guess the question comes is, could these could there be a possible relationship between the sediment geochemistry and perhaps mineralization? These eucinic sediments could be perfect in situ traps for perhaps secondary metal-bearing hydrothermal fluids. So I guess to quickly summarize again, we use the multi-proxy approach for more robust interpretations. And hopefully in the near future, we can couple that with isotopic analyses and sedimentological data for a better understanding of what's actually controlling these changes. And hopefully we can apply these proxies at other samples at different localities too. And I guess to quickly conclude, this is where I'm sort of at with these different themes. With theme 1, I'm well into finalizing a draft for a manuscript and just waiting on some revisions and last bit of analyses. And hopefully we'll be able to apply this method in other shales within the Greater MacArthur Basin. And in theme 2, I think slightly more work needs to be done. I'll be hoping to collate other previous work done in similar units outside of the 2 different drill cores. I know Kunban and Al have also done carbon isotopes in similar units. And hopefully we can keep trying to ground our geochemical analyses with sedimentological observations and perhaps with couple that with redox proxies too. And in theme 3, I think even more work needs to be done. There's preliminary results really, and hopefully we can couple that with isotopic analyses and correlate with samples further away too. I guess for the rest of my PhD, I'll hopefully apply these different themes to other bits of the Greater MacArthur Basin, such as the South Nicholson. Oh, don't want to do that. Such as the South Nicholson, which I'll hopefully be able to get samples on from the MinEx CRC drilling program sometime next year, and maybe the Tompkinson province. So yeah, thank you so much for listening, everybody.